Welcome! Today I'll be talking about proving triangle congruence in geometry. In proofs, triangles can be very helpful and can be used in algebraic applications or for proving sides parallel in quadrilaterals. There are currently 8 ways to prove triangle congruence, with 4 of them occurring in a very specific situation. The first 4 apply for every triangle. They're called side side side, angle side angle, angle angle side, and side angle side. To understand what these theorems really mean, let's just look at the diagram over here. For angle side angle, you can see the side here and then the angles on each ends of the side. The corresponding angles are congruent, indicated by the congruence markings, and the side is congruent to its corresponding side on the other triangle through the congruence marking. That's basically how we prove a triangle congruent through angle side angle. Through this, you should now know how the theorems work, and if you don't, feel free to leave a comment below and I'll happily answer it. Now, some of you might be wondering, why can't I use angle 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 or side side angle? For angle angle angle, the triangles will be similar, yes, but the actual sides won't be congruent. For side side angle, you'll have two sides congruent, and you'll have the angles congruent, but the last side can be placed in two different locations, meaning that it cannot be used for proving triangles congruent. Now, how does proving triangle congruence help us? After proving triangle congruence, we can use a theorem abbreviated as CPCTC. Corresponding parts of congruent triangles are congruent. In this example, if we had to prove that angle 5 is equal to angle 6, we would first have to prove that the triangles are congruent, and then we could use CPCTC to say that the angles are congruent. Let's try fill out a 2-column proof with this. For this diagram, we're given that line segment A to C is the angle bisector of angle DCB and angle DAB, and we have to prove, like I said earlier, that angle 5 is congruent to angle 6. Our first statement would be, obviously, the given. But for our second one, let's analyze the given. It is said that line segment AC is an angle bisector. So wouldn't that mean that angle 1 is congruent to angle 2 and angle 4 is congruent to angle 3? Yes, it does mean that. So let's place that as our second statement. Now for our third statement, we need to analyze the sides given. There's no way to prove that DA and AB is congruent right now, and there's no way to prove that DC and CB are congruent as of now. The only line we have left is A to C, and we can easily prove that it's congruent to itself through the reflexive property of equality. So we have to state that AC is equal to AC. Now some of you might be thinking, well that's dumb, I know that something is equal to itself. However, in a geometry proof, it is necessary that you state it before you try and use a triangle congruence theorem. So that would be our third line, reflexive property of equality. Now for our fourth step, let's look at what we've got. We've got one pair of consecutive congruent angles. We've got another pair of consecutive congruent angles. Right in the middle, being our angle bisector, we know that it's equal to itself. So can't we use angle side angle? Yes, we can. Angle 1 is corresponding to angle 2, angle 4 is corresponding to angle 3, and both triangles share the same side, so we're able to use it. So our next step would be triangle ABC is congruent to triangle ADC through angle side angle, and then finally we can say angle 5 is congruent to angle 6 through CPCTC. Now, onto the specific situations. A right triangle is a pretty special triangle in which it has its own 4 sets of proofs for it. A right triangle can be proven congruent through hypotenuse leg, leg angle, leg leg, and hypotenuse angle, but teachers mainly test on hypotenuse leg. For the hypotenuse leg theorem, it states that if the hypotenuse and leg of a right triangle are equal to the hypotenuse and corresponding leg of another right triangle, then the triangles are congruent. And if you think about it, it's essentially the side-side angle theorem, which we said wouldn't work at all. However, this is a special case. Whenever it's a right triangle, side-side angle would work, no matter what you do. Let's look at this example over here. We're given a 2-column proof that we have to fill out over here. The given states that line segment AC is congruent to line segment BD, and here I wrote LSAB, but that essentially means line segment AB, so it would fit in the two-column proof. But on an actual test, please don't write LSAB or something like that. You would lose many points. Anyways, line segment AB is perpendicular to line segment BD, and line segment AC is perpendicular to line segment CD. And we have to prove that the two triangles ABC and ACD are congruent. Well, our first course of action would obviously be to write the given. But then as always, let's analyze the given. It says here that these lines are perpendicular, AC and CD, and AB and BD. And now, what do perpendicular lines form? That's right, they form right angles. So angle ACD and angle ABD are right angles, with the reason being definition of a perpendicular line. Now, as you've hopefully learned before, any triangle containing a right angle is a right triangle. So we have to define that in our next step. So our next step would be to write ABC and ACD are right triangles through definition of a right triangle. Now, let's analyze all we have so far. We see that these triangles share a side. Now we know that both of these triangles are right triangles. We know that line segment AC is congruent to line segment BD, so we have two sides congruent. And the side that's shared is actually the hypotenuse. So we can say that the hypotenuse is equal to itself through a reflexive property of equality. The answer for the final step should be pretty obvious now. We have corresponding congruent sides and a hypotenuse that's congruent. Remember the four theorems we just talked about? Do any of them work with this triangle? Yes, one of them does. The hypotenuse leg theorem. We know that these two triangles are right triangles, and we know that the corresponding legs are congruent. So we can say that triangle ABC and triangle ACD are congruent through hypotenuse leg. Thank you for watching, and if you have any other questions or concerns, please leave them down below and I'll be happy to answer them.